One of the ways we can predict an enthalpy of reaction is by considering all of the bond energies over on our reactant side, and then all of the energies on our product side. We can ask how much it takes to break all of our bonds, how much energy it takes to make all of our bonds, and look at the difference between those two. Now, for an illustrative example, let's go ahead and use H2 and O2. We're going to have both these be gases. We're going to then light them on fire, and we're going to generate water vapor. We know that it's likely to be vapor because these were both gas phase, and we're going to be producing a bunch of heat, as you've seen anytime that you've seen hydrogen caught on fire. The Hindenburg videos would be a good example of that, when the blimp or dirigible just caught on fire. Now, if you need some practice balancing the equations, go ahead and pause and give it a quick balance. Okay, so let me go ahead and do that. We have 2 hydrogens, 2 oxygens. On this side I have 2 hydrogens and 1 oxygen. That's an odd number. I'm going to go ahead and multiply this by 2 to go ahead and get it to be an even number to match up with the even numbers that I have over here. I've got 2 oxygens. That matches up. I have 4 hydrogens total. That doesn't match up yet. I put a coefficient of 2 there, and I'm set to go for my balanced chemical equation. I don't know how much heat energy I've got, but we can figure that out right now. So hydrogen is going to have a single bond. We're going to go look up the energy for a hydrogen-hydrogen single bond. Here we're going to look at an oxygen-oxygen double bond. And notice that I'm saying the word twice. It's because I'm talking about oxygen double bonded to another oxygen atom. I'm not just being redundant or stuttering on that. So when we look those numbers up, we'll get these values here. I'm going to go ahead and move this up since I'm writing over top of my text. There we are. So if we know that a hydrogen-hydrogen single bond is worth 436 kilojoules per mole, and that we have 2 molecules with that bond, then we're going to have to break 2 of these bonds total. Here I'm going to have to break this double bond for oxygen. I only need to do it once because my stoichiometric coefficient is 1. And when I add these up, I'm going to get 370 kilojoules per mole. Now, I do want to highlight one thing. I didn't look up the value for the oxygen-oxygen single bond and multiply by 2. I used the oxygen-oxygen double bond. The 2 values are not going to be equivalent. The first bond is an end-to-end orbital overlap, like this. That's a sigma bond. The second bond is a pi bond, and that's when you have your 2 p orbitals doing edge-to-edge overlap. That's not going to have as much overlap. It's not going to be as strong. So a second or third bond doesn't add as much energy into the bond strength as your first bond does. So let's go ahead and see what's going to happen on the other side. Now, in water molecules, we're going to have a hydrogen-oxygen single bond. Each of those will be worth 464 kilojoules per mole. Again, I didn't memorize that. I looked it up in a table. And I've got 2 of them, meaning that in a single water molecule, I've got 928 kilojoules per mole worth of energy. In my second water molecule, I have the same amount. Multiply that number by 2, and I end up getting 1856 kilojoules per mole. So I started out with 1370 kilojoules per mole of energy that I'm going to put in. I get back out 1856 kilojoules per mole. Now, it seems a little counterintuitive to people sometimes to think of making bonds as giving you energy. But keep in mind, the reason that they bonded in the first place is that they weren't as stable as they could be, the atoms that were by themselves. When they snapped together, they became more stable by sharing their electrons. So becoming more stable means that you're going from a high energy to a lower energy. And that means that it's going to be an exothermic process. And so we're actually going to be recovering energy by allowing these atoms to snap together. If you want a visual to picture in your hands, grab 2 magnets and stick them together. You put energy in to pull them apart. Then they become more stable when they snap back together. That's the kind of thing that we're talking about here. Now, when we work it out, we can figure out our enthalpy for the reaction. I started at 1370 kilojoules per mole. I'm going to end up at 1856. But here's how I like to handle it. I don't like doing it as a math problem, or at least initially I don't. I like to think of it as I'm going to put in 1370 kilojoules per mole to break apart all of my bonds in order to get my atoms with their normal number of electrons from the periodic table. Then I'm going to get back the amount of energy that I released by letting them snap back together. And in this case, that's going to be worth 1856 kilojoules per mole. So I'm going to have 1370 minus my 1856. I expect to be at a lower energy. Negative energies mean that I have energy leaving my system, which means I'm going to be releasing heat, and that's exactly what we communicated up here. So I'll do 1370 minus 1856. So 1370 minus 1856 minus 486 kilojoules per mole. So I'm down 486 kilojoules per mole. So that would be the enthalpy for this reaction. It'll be a negative sign because it goes downhill energetically. And so this would be the number that I'd report as the enthalpy of reaction to form water, also known as the heat of formation for water. Now, this is what we'll describe as using our bond energies and Hess's law in order to determine an enthalpy of reaction one bond at a time.